Ladies and gentlemen, welcome. I've been to this show many times. I have this t-shirt from, I think, 7 or 8 years ago, on the 40th anniversary of shipping the Atari 2600. And my children say, "Dad, you were cool once." For working on this stuff. So, I am failing retirement. I turned 75 this month.
Congrats.
And I'm entering my 10th year as a professor at the University of Washington Bothell campus. He's one of my former students. And I joke with them, they're smarter than I am, but I've forgotten more than they've learned so far. But I'm here now because I worked on 3 generations of animation machines, and this is a book about one of them. So I'm going to go to the agenda. How I got here. There are books about 2 of them, and I'm working on the 3rd book. And so I want to talk a bit about game design, meaning play and graphics and sound, game implementation methods, game testing methods and resources. There's probably some items I forgot to mention, like APIs, but we'll get there. So how I got here, I've actually, must confess, never been a gamer myself. I was working in medical electronics in the summer of 1973, and I went to a conference in New Orleans to give a talk about my research work, which is building respiratory monitoring equipment for intensive care. NIH canceled our contract, so I lost my job, and I needed to find another job. And I found 2 jobs. By cold calling, I found a job in Orange County, California, putting microprocessors inside respiratory monitoring equipment. If I had found no other job, that's what I would have taken for 2 good reasons. Besides my background, my family is driving range from Orange County, and the surf is really good in Huntington Beach, which is where I surfed a lot in the 60s. But I found a job through my network with Atari. And I took it not because I'm a gamer, but I took it because I was going to apprentice to a guy who was going to teach me large-scale integrated circuit design when that was a brand new hot thing. It was so hot that it was hard to learn it in graduate school. It was really cutting edge. And so I was going to work for that guy. First result, the 2600, which you've probably heard of by now. We have a bunch of them on display over in Hall E, the retro computer area. Second result, the Atari PCS. And my student Hunter here is part of a team that ported a new game to it and demonstrated. We have that over in Hall E. And the third result was the Amiga computer, which was a monster for one. It had the first GPU. I know this because I've been dragged into court to testify to the validity of that patent. I'm grateful that the patent is expired. I don't hate lawyers, I just wish they were bored. So there's a cartoon history of video games, and someone drew a cartoon of me and Jay. Obviously, my hair was longer and darker. I'm older now. These things happen. I gave my original version of the 3 generations of animation machines at the now defunct Living Computer History Museum in the Seattle area. This was before Paul Allen died. So there's a 2600, there's an 800, and there's an Amiga. So there are books about them. MIT Press had some historians research a book called Racing the Beam, because that machine was so old and so primitive that the programmers are basically racing the electron beam down the screen. And the third book on the Amiga was called The Future Was Here. Another historian wrote that. So, given that, I think there's a missing book in what would become the J Minor trilogy. And so I've been working on that book. It would be a sequel to Racing the Beam. It would be a prequel to The Future Was Here. It would begin with the lessons that we think that we learned from the success and failures of the 2600. And it would end with what we learned from shipping the Atari 8-bit computers going forward that would animate our third system. So here's those books. I have them right here. I'm going to have them over in Hall E. You can look at them, but please don't walk off with them. I've bought a few copies. And so the third book, I did my first draft 11 years ago, about 12,000 pages. I've drafted part 1, which starts with, here's the lessons we think we learned from the success of the game console. And it will have a lot of development stories and try to credit lots and lots of people. In fact, one of them was Dave Crane, because the 4 founders of Activision were the 4 best programmers that we had in-house at the time. And after they shipped a bunch of games that sold well, we drafted all of them to work on the BIOS for the insides of the Atari 8-bit computer. Another story for another day, we designed that BIOS so it was extensible. 40 years after we shipped it, Tom Cherryholmes and company started developing the FujiNet devices, which were network adapters for that machine. We didn't know what to extend it for. He figured that out and did it 40 years later. There are probably several FujiNets on display somewhere in this place. Anyway, that's the first piece. The third piece would be what happened to it in the market. And one of them is that Atari has bought up all the intellectual property of the old Atari, and they're selling new machines right now. Dave was just remarking about how unhappy it is that they're doing it in emulation rather than live hardware, but you can buy now boxes that run off of USB-C power and drive HDMI. You can buy, similar to an Atari 400 Mini, that's a new version of that 8-bit computer. Now, we have it in booth E. Stepping into the center, the piece of the book that I consider missing is how to write retro games for this machine on this machine, because it was designed for that. So the lesson is, first lesson is trying to be cheap. We put the control of the vertical in software or in firmware rather than in hardware. There's only 128 bytes of RAM in that machine. I mean, it's tiny. I have a cartoon somewhere that has a cartoon of it and it's saying, I have no memory, because it doesn't. So our conclusion was that our second system, well, the first system, by putting the control of the vertical in the software, we allowed the programmers to do things that we, the hardware people, hadn't imagined. So they went much farther than we expected them to. A nice surprise. We expected this machine to last only 2 or 3 years in the market. It lasted a dozen. They're still selling software for it now, and it's been, what, 48 years since it shipped? I mean, that's almost half a century, right? So our conclusion is our new machine shouldn't simply be a bitmap and a processor to animate it. It had to allow the game designers to step around other limitations and reconfigure things on the fly a lot, because they're smarter than we realized that they were. And we had to give them room that they're going to run with. So we consulted guys like Dave Crane, when we were designing this new machine, and he gave us ideas that we incorporated into it. So we had created a platform for other people's art, because the founders of Activision were artists trained as engineers. And we thought we needed to move fast because we thought our competitors were going to try to eat our lunch within 2 years, and they certainly tried. They certainly tried. So in the development, you can, like I say, Atari Age, they're selling these things right now, and they're still developing new cartridges for it now. A buddy of mine, Ed Fries, 25 years ago, he developed Halo for the original Xbox. He did a port for the 2600. It's playable. The graphics are clearly inferior, but it engages people in the fate of their avatar, which is what games are about. So we had, going into this new machine, 2 overlapping requirements. One of them, it had to be a great animation machine, second generation. But it also had to be a great computer. What we wound up doing is building 2 packagings of the same chipset, one as a game player and one as a computer. And then one of the chip designers, Doug Neubauer, his chip worked the first time, and he was bored, and he's really smart. So he wrote Star Raiders, which is probably the best original game for that platform. And that blew marketing away. And they said, we can't ship this thing without integrating some kind of, at least a membrane keyboard in this machine. So they put a membrane keyboard in the Atari 400, and it still got it. The people who wrote the BIOS for that system includes Dave Crane, who was sitting here minutes ago. Now, writing retro games on this platform. All of you are attendees at a Retro Games Expo, so all of you have a good intuitive grasp of what's in the game. It's not simply a display, and it's not simply a sound. You have to place the player or their avatar in some kind of tension. They're trying to do something, either against the game itself as a one player or against another player in a contest of some kind, right? I don't need to explain that. You all got it. So you have some goal, and you have to illustrate that with some video and some sound. You ever played a video with terrible sound? You know what I'm talking about. As an aside, so the original inventor of video games, in my opinion, was Ralph Baer. And I had a chance to meet Ralph Baer in 2014, just before he died. So he built this machine at Saunders Associates. He called it the Brown Box. And it had 3 things, two paddles moving around, and a third thing that was kind of the ball, right? And that was, Saunders Associates licensed that to a defunct consumer electronics company called Magnavox. And they brought out the Magnavox Odyssey in 1972. And Nolan Bushnell, founder of Atari, saw a demo of it. And he came back and he told his chief engineer, his only engineer, good game idea, terrible implementation. It needed color, it needed sound, because it didn't have sound, and it needed a score so that people could tell who was doing better, right? To make it a game. And that was Pong. Somewhere on the floor today, I saw a copy of the original arcade Pong. They installed that in a bar, Andy Capp's, I think, in the Silicon Valley. And after 10 days, they called up Alan and they said, it doesn't work, come fix it. Alan went to go fix it and discovered that the reason it didn't work was that the coin slot was completely full of quarters and it wouldn't take any more. So he filled his pockets with quarters and he said, call me if that happens again. So that was how Atari got going. And I tell that story to amplify that it's important not only what you display on the screen, but what you hear. And so, for example, in the old Pong games, and in my implementation of Pong on the VCS, the sound got higher and higher frequency as the score got higher and higher to reinforce some tension, right? So, let's step back. In this book, I want to put in how to develop games for it on it. What I have not done much yet is made them have to reinvent the gameplay. Just reinvent how to do the sound and how to do the video, right? So the first team took Tank from the 2600, and they made a 2-player on the 8-bit machine. That's done. We're not going to talk about that much today. The second team used the now available computer power to be the machine, so you could have a 1-player playing the machine. And one of the interesting parts about that was, I of course asked the students to do gameplay testing with their fellow students, right? And this implementation beat half the other students and lost to the other half of the students. So I'd say the difficulty was about right. You follow what I'm saying? The third team, represented by Hunter here, ported the Superbug arcade game to this Atari 8-bit machine. And he's going to talk a lot about that. I have put in a bid for some undergraduates to port a fourth game, which will be more complicated. I assume that many of you have seen the game Ready Player One, right? And you know that the third challenge in that game is to play Ready Player One, not to win it, but to find the Easter egg. So I will invite my students to port Adventure to the Atari 8-bit computers and put in their own Easter egg, or Easter eggs plural. But that's another story for another day. To think about what software is doing in a 2600 game. So it was designed in the old days when we had raster scan video. So you've got an electron beam. Maybe if you're lucky, you've got 3 different colored phosphors, so you can get color rather than black and white. And the beam is going back and forth, and there is a short period, very short period, when it's retracing from one side to the back. That's horizontal. And there's a longer period when it turns off the video and moves the beam back up to the top of the screen. Turns on, starts writing again, right? You all probably remember CRT TVs from when you were small, right? So that's what it did. And so what it would do, this was a line-oriented machine, no bitmap, no character map. So it spends all of its display time writing and rewriting the hardware like mad. Dave Crane can tell you long stories about how to do that or how to not do that. In the vertical blank processing time, it's reading what touched what the collisions were, and what the positions were, and trying to decide the next thing that should happen in the game. Is this tank going to go here, there, or somewhere else? Is it going to explode? Is it going to jump backwards? All the other things that could happen in a game. It makes those decisions, and then it displays it again. So far, so good? Lost anybody? All right. So, in that development, we were using 6502 assembly language. For those who have not programmed in low-level assembly language before, there's a one-to-one correspondence between a line that you type into the assembler that turns it into object code, making the bits that the hardware actually interprets. High-level languages are nicer. They were invented 60 years ago because programmer productivity was a lot higher when you had fewer lines to type and fewer typographic errors to make. Typographic errors happen all the time. And, you know, so we went to, BASIC was built into personal computers of this era. C language was possible in that era. Forth was a language I would rather forget. It was quite compact. I have a notebook here that's got Bill Gates' address and phone number from Albuquerque, New Mexico, when he came to visit us to sell us BASIC. This is before he got into the operating system business, a long time ago. And we would use logic analyzers. Does anyone know here what a logic, show of hands if you know what a logic analyzer is. I see several, okay. Logic analyzers are devices that watch a lot of bits in parallel. So they watch the address bus, they watch the data bus, so that they can tell you in detail what's happening. They're much less common now because everything is hidden down inside things that you can't get your clips on. But we used them a lot at that time in history. And we used a 1611 because it would clip on to the address and data buses and disassemble it on the fly. So you can see you had a better chance of figuring out what your stuff was doing. That's what happened in the 70s and 80s. Now, at that time in history, you might have a monitor or a reset or NMI button so you could halt its execution and then feed out of it what the memory looks like and trying to figure out what your problems are, because bugs happen, believe me. Anyway, given that, new methods, I'm leading up to Hunter here. So now we have computers that are several orders of magnitude faster. I mean, the machine we're targeting was 1.8 megahertz by 8 bits, right? And now we have emulators that run on PCs. Mine here is north of 2 gigahertz times 4 processors times 64 bits each. So this thing easily runs very powerful emulators. So they behave as fast as the old machine, but they're not. And so they're executing the logic in software rather than in hardware. But they emulate memory, and they emulate all the other registers. So people debugging things can stop things anywhere and see everything that would otherwise hidden from the game developers of decades ago. So outlining the new methodology, they use CC65, C language compiler. Again, so you write a lot fewer bits to say the same ideas. You debug in Altera emulator or another emulator. Then you can generate an XEX file, which we can demonstrate over in room E. And we have little boxes that emulate floppy disk drives, except they use mass, semiconductor mass storage. So they're much more reliable. They don't need to be cleaned. And test and demonstrate it on live hardware, which you're welcome to do later. So I want to hand
Hello, I'm Hunter. I'm a Professor Decuir student. I'm a computer engineering major at the University of Washington, Bothell, and I was tasked with porting the Superbug arcade game to the Atari 8-bit PCs. All right, so here's our problem statement. He came to us saying that he wanted to write this book about writing programs and games on the Atari 8-bit PCs. So this was a screen cap of the original Superbug, which was on the big arcade machines. And it was our job to redesign it in a way that it could be played on the Atari 800. As you can see, it's a little different. The machine that is the arcade machine included like a steering wheel and a stick shift, which is not something that's on the PCs. So that's something that we had to address. And so our design methodology was, which he spoke about a little bit, was we wrote the game entirely in C and then used the CC65 compiler to turn that code into a .xex file, which It was also convenient. We had the Atari emulator, which could be ran on any Windows computer, so we could test it just like with our laptops without the native hardware. But then we could also take that XEX file and port it and to make it work directly on the hardware itself. So that's exactly what we did. And for the changes that we made were ultimately we wanted to make the game fun, replayable, presentable, and capture the essence of the original arcade game. All right, and what he spoke on a little bit, we were able to directly see the registers, which was very helpful, a very helpful tool that was available to us. We were able to mark, is this value updating appropriately? Let's look in memory. So things like that make it way easier to develop these games than what was probably available to the original Atari developers. All right, so ultimately we were able to successfully remake this game, and it included a tile map and a display list, and we were able to demonstrate tile scrolling so we could see the car drive on the track, and we also showed how to put sprites, animations, as you can see, the scoring and fuel logic, and we were able to document fully how it's made. There are definitely other games that have a lot more cooler mechanics, but for what we have, I think we did a good job demonstrating what certain fundamental mechanics so for people to make their own games. All right, yeah, and we had a pretty fun game testing day. We had a campus security playing the game. Very happy about that. But overall, it was very well received. It was fun. Yeah. There's a link to the video here as well. All right, yeah, sort of the conclusion here. I will say that it's definitely, C is much more well-known than assembly language is. However, like using this method, the compiler sort of acts as kind of like a black box. So even though C is easier to write in, I would say you would probably have a better time writing it in assembly if you were to understand that, just because it's easier to debug and you don't have that like mystery of where the compiler is placing data in memory. And that was a little difficult, but overall, I think it was a great project, and I think we did a good job on demonstrating how to implement these functions in 8-bit games. All right. Oh, but of course, there's always potential improvements into the game. Of course, you could have added obstacles and things like that, or different controller compatibilities. But oh yes, and more colors as well. Make it more graphically presentable. We did have 6 months to make the game, so that's some time, but that's also to learn the system and then get together and then develop it and implement all these functions. Future work, future revision. All right, and as our thank you to Professor Joseph Decuir and everybody who play tested it. Yeah, all right, thank you.
All right. So there's obviously, I haven't actually finished the book yet, but I'm planning to incorporate their work. So they did a lot of the work on GitHub, and so when the book is published, it'll say, here's where the stuff is for the tank games, for the Superbug game, and for the adventure game when we finally do it. So people, I don't have to set up a separate website. I can point people at this stuff. Because my invitation, of course, would be to explain game design, say, download this stuff, make sure it works for you, and then build on it however you want. Because that would go back to the original lesson. We're creating an artist's tool for new people, interactive cartoons, essentially. And you're all here because you like those cartoons. So resources would include the technical reference manual, which is on the web, the Day Ray Atari by Chris Crawford, who actually lives in Southern Oregon, who wrote, in my opinion, the best book about how to program games for it on it. The Altera's hardware reference manual, the breakout book on the next slide. A friend of mine wrote these two books, and I like that one as the best substitute so far. I've written an article for the IEEE Consumer Electronics magazine which is a summary of what goes in the book. And there is a YouTube video from Vintage Computer Festival East 6 years ago on this machine, on the 40th year of shipping that machine, and it's on YouTube there. Do I need to hold that still so people can copy it down, or can it get published somewhere? Are the results of this conference put on the web? No? Yes? Right.
Eventually, I think.
Eventually. So that's me and Hunter. And so we have plenty of time for Q&A. Yes, sir.
Yes, I have a question. So nowadays, the AI systems like Copilot can help generate some of this older 8-bit code. Did you guys use that at all to help you in the SuperPet stuff?
Not that I'm aware of.
We definitely tried, but
Okay.
it's poor results.
Okay.
I'll say this.
Okay.
Parenthetically, so I have a different sets of capstone teams. I have a neighbor who has a company called Inksys, and he models AC power systems all over the world. He's got very good models that cover the United States, for example. So he can predict uses and prices in real time. And he can predict it not only at 1 second interval, but he's getting towards 1 millisecond interval to prevent instabilities. Now, the original code was written probably 5 decades ago in Fortran, and it was ported to Visual Basic sometime in between. And now they're converting it to Python. And what the students have discovered repeatedly, if you give the whole model to Copilot, it makes huge messes. You have to understand the structure of it and simplify the pieces down so that it doesn't make a mess. And then carefully test and integrate the pieces back together to build an entire system that now works again, but works in Python rather than Visual Basic. That's what they're observing so far.
That's what we've observed so far.
Okay, so great minds thinking alike. Yes, sir.
You mentioned that debugging when using C is more difficult than assembly. Could you go into a little more detail about why that is?
Yeah, so there was a lot of, we found there was a lot of.
There's the mic. Talking to the mic. They're both live.
Oh, is this on? Oh, perfect. Yeah, so we found that with using the compiler, we couldn't really see like where the data was being saved in memory for everything that was not like directly assigned. So because of that, I would say that's not something you would see in assembly. So with that behavior that you can't really observe, I'm sure there's something that there's some reasoning behind what was going on. We just weren't able to figure it out. So that might be like reflective of our inexperience, but that's sort of what we found.
So short answer, there's no high-level debugger in the environment, basically, right?
Right,
Yeah.
exactly.
If there was a large enough market, someone would create one, but there isn't a large enough market. More questions, ladies and gentlemen. Yes, sir.
So I'm mostly a Commodore guy, but I was recently working on a 600 XL,
Mm-hmm.
and I discovered that the video chip on that has an analog chroma output, but like a 4-bit digital luminance output.
It's true.
And just coming from Commodore, they always had analog output on both.
Right.
What was it a limitation, or why is that?
We were summing it in that generation. We didn't have good digital analog converters on chip, so we brought out 4 separate bits to sum outside. Does that make sense? And what was true in all the Atari and the Amiga work is you're producing a relatively narrow bit stream, 1 or 2 bits tops, and then you turn on a palette register. And the palette register will have bits that determine color, bits that determine luminance, and in the case of the Amiga, bits that determined saturation as well. Or we switched over to RGB. Of course, by the time we were building the Amiga chipset, we had good digital analog converters on chip. We didn't in the Atari days. One of the things I did when I left Atari in '79 was started graduate school at Berkeley, And I was trying to learn how to do analog stuff in NMOS. Mercifully, we all invented CMOS, so analog got a little bit easier. I actually designed a depletion mode NMOS op amp at Berkeley, and I'm glad it's history. Did I answer your question?
Yeah.
Good. More questions? Yes, sir.
Yeah, more from Hunter. How did the program size of your port compare to the original size? And did you take advantage of any like in-place memory operations? Did you have to?
What do you mean by in-place memory?
I mean, you instead of using like a buffer, like you used did some like pointer operations so that like you didn't have to use more memory to do this operation. You could use less. I'm just talking about like memory management efficiency.
There was a lot of consideration taken into the memory management. There's only 48 kilobytes of RAM that we have available, but there wasn't too much of an issue with running into the limit. I'm not entirely sure of what what the size of the original one was. We had access to like the emulated version of the game, so we know how the game worked, but we didn't have access to the actual source files of the game. But the big thing was the tile map, probably because it was 200 by 120 bytes. That's a lot. That takes up about half of the available RAM. But the big issue of that was where the memory was being placed and making sure it wasn't conflicting with other hardware registers and things like that.
Right. So, yeah, okay.
Yeah, another question. So the question for Hunter, so did you end up having to hand code any functions in assembly to get the speed or the size that you wanted, or was everything entirely done in C?
Well, we wanted to do everything entirely in C to show off the development environment.
Okay. But did you find, though, that there were scenarios where the compiler just wasn't as efficient from a speed or memory standpoint, and you just dealt with it?
Largely, we just kind of dealt with it, but looking back, we probably could have approached that in assembly as well, definitely.
For perspective, so the 2600, very little memory, and a lot of the competitors to the Atari PCS had character maps or bit maps, and the PCS had a secondary processor running alongside the displayless processor. So you could format and reformat the screen on lines or sets of lines at a time to build very complicated things, for one. And for two, into this system, we designed the ability to move things horizontally smoothly and vertically smoothly, which is what they used and what the people doing Adventure will use, and which is what the people who designed the NES used. Because the arcade people were doing it. In fact, one of the reasons that I characterize Dave Crane's software as one of the best original games for the 2600 is it did horizontal scrolling. And Carol Shaw wrote River Raid, which is an aircraft flying vertically and back and forth, and so it's smoothly doing vertical scrolling. So we looked at those as original games on the 2600 and said, okay, how can we do that more smoothly, more easily? And what Superbug does is imagine you've got a large screen and you're windowing what you're seeing, so you can have a larger space. And that whole idea is used constantly now in video games everywhere. It was a great advance at the time. Yes, sir.
What was the maximum possible program size on a 2600 program? And
Well, the 2600 without bank switching was only 4K.
yeah.
And they could bank switch it to go farther. I had an epiphany in early 1977 because we'd just come back from the CES show in Vegas, and I realized these games are a lot better than we imagined that they were going to be. This is going to last long. What happens if we sell a bunch of game cartridges to people? and we come along with a machine that's not compatible, what are they going to do? Are they going to abandon Atari? Or are they just going to abandon the 2600 to buy another set of game cartridges for a new platform? I mean, the problem of compatibility has arisen repeatedly in the computer world. Pick another example. How many of you remember the 8080 processor? Way back when, right? So that was $100 a piece in 1975. And so people wrote application software and operating systems that use it, like CP/M. So Intel then started considering what happens when we move forward. So they made the 8086 assembly code compatible, but not object code compatible with the 8080. So that companies like Digital Research in Monterey could recompile CP/M for 16-bit. It was different object stuff, but it wasn't very hard to debug because it was the same assembly code source. And in contrast, Motorola brought out the 6800, and I said the 8080, and they decided to make a complete break to the 68,000 family, which was widely used for a very long time after that. It was used in the first Mac, it was used in the Amiga, it was used in a bunch of other popular machines at the time. My epiphany at Atari was, we should add $1 to the material cost of the 2600. We should make 30-pin rather than 28 or 24-pin cartridges. And we should buy a complete 16-bit address rather than an attenuated 6507 that can only handle 13 bits of address. Because I wanted to design a system that could have a roadmap where we could build future machines that were backwards compatible with the original games. So that our customers, if they bought a lot of our cartridges, wouldn't feel as strong a need to abandon Atari when they went forward. You follow what I'm saying? I had this epiphany in January of '77, and management said it was too late to make that change. So our second system was not compatible, so people had to buy new cartridges. Now, obviously it was more powerful, and it could easily port things that were difficult to port from the arcades. You could go to see our exhibit over in Hall E later, and I can show you what the 8-bit computers port looks like versus the 2600s port, and they're clearly better. But we're forcing people to buy new games again, and they're not going to like that, and they didn't like that. And so when we, in fact, replaced it with a machine that was not compatible, they had the chance to abandon us for Intellivision or for any other machines that came along. And we neglected to include any kind of security in the system. In fact, the 26 has no ROM in it at all. So it has no way of telling whether that's an authentic cartridge or not, whatever that means. And one of the things that happened in the early 1980s was there was this explosion in different titles for the 2600. Some of which were great and some of which were junk. Lots of junk. And that market imploded, for those of you old enough to remember, in '83 and '84. So Atari was dismantled and sold by Warner Communications. The game part got basically loaned to Jack Tramiel as Atari Corp. And the rest, the arcade people, was sold to Namco in Japan. And after a year of catastrophe in game marketing, Nintendo came in with the NES and scooped up all the pieces a year later. And their system had ROM built into it, and the ROM would read an encryption chip that had to be in the cartridge. And the ROM would not run the cartridge unless that encryption chip was there. The only way to get the encryption chip was to pay Nintendo $5 a piece for it. So Nintendo controlled the market for NES games. And they successfully argued in court that this was not a restraint of trade because the whole market was aware of the collapse of the 2600 game market a few years earlier. And they said, we need this technical solution to control the quality of the games that are being shipped. So the courts let them get away with it. Anyway, another story for another day. Question?
I was just wondering what, in your opinion, drove the executives at Atari to not listen to the compatibility issues from a marketing standpoint? Like your opinion on it.
Well, I was talking up through engineering management, and engineering management said if we're going to make our shipping deadlines, because it was 1977, we needed to be in mass production in the summer. It was too late to change all the packaging, all the purchasing, the circuit boards, the works. I mean, we had already gone through FCC Part 15 certification. We'd have to do it all over again. So, in fact, my epiphany was too late from an operational standpoint. And for those of you who've been in and out of the consumer electronics world before, a lot of things are driven by holiday purchasing. So I stayed at Atari. The last things I did on the 2600 were to write the code that they used in production for quality control testing. If you're going to engineer for quality, you have to separately test for quality assurance. How do you prove that the first prototype works? And you do part 68 and part 15 testing with that, et cetera, et cetera. And then you have to do quality control testing on every single manufactured unit. We made 250,000 of them in the first year. We made 800,000 of them in the second year. And we made 30 million over time. And that's a lot of QC testing, because you don't want to put crap in the box, right? And this is before the internet, when you could trash a device only to the people that you know rather than to everyone. Now you can trash it to everyone. Did I answer your question?
You did. It sounds like you guys just ran out of time.
Well, we're driven by the calendar. And, I mean, they eventually got that message, and they eventually designed the 7800, which was an upward compatible machine. But they came out with that in 83 or 84. That was too late to solve that problem. And every game manufacturer has the same problem of, at some point, are they preserving people's investment in their game libraries or making them abandon them and move forward? And I was a young engineer. I didn't really understand marketing yet. I learned. Let's see, what's the time? I'd say we should be wrapping up. Another 2 minutes. Any other questions? Yes, sir.
What was true in the game development back then that's still true now that you wish was not true?
Well, a big piece of it, I think, is how do you come up with an interesting game conflict problem to solve? The separate problem that I'm trying to address with my book is we designed that machine to be easy to develop games for on. And some people developed a lot of games for it on it, and for C64s and other devices of that period. And I want to encourage people to do it as a hobby, not for a living. One of my sons went through and got a degree at a school called DigiPen, which is affiliated with Nintendo of America. And he learned to be a video game designer. He couldn't find much work as a video game designer, so he now works as a network engineer for a voice over IP company, right? He's got a 7-year-old son one of my grandsons who wants to design video games. So the need is still there, but I want to make it practical to take publicly available code, explained in a book, download it, test it, run it, start thinking, I want to make some changes. I want it to do this. I want it to not do that. And start experimenting. Start being hobbyist game developers. Now, Atari Age is out there helping people to design 2600 games because there's a larger market. But the emulators are really good for the 8-bitters. The emulators are really good for the Amigas. They're much more powerful machines. And the modern emulators are so fast and they can do any of those things. So what I fundamentally want to do is make it so you don't need 100 man-years to do a new game. Make it so you can do it in the season for fun because you want to show it to your kids. And maybe they'll think you're cool.
Where can we follow the progress in your book?
Well, I gave MIT my first draft in 2014. But I was still working professionally. My wife was still alive. A year later, I got laid off and my wife got cancer. So I spent a lot of time in cancer care and I spent a lot of time as a professor with guys like Hunter. And they keep loading me up with stuff. And I'm an old guy. You know, if I lived in the Serengeti, the lions would get me. So I don't have the energy that I used to have either, but I'm slowly working through it because the pieces I have written are pretty good. And I'm cooperating with the people who do Antic Podcast to update the history parts. And I'm working with my students to write the game development parts. And when I'm ready, I'll send it back to MIT Press.
I'm sorry, I was asking, where can we follow your adventure? Do you post it anywhere? Blog?
It's not on a blog. That's my email addresses. I'm also on Wikipedia, and I'm also on LinkedIn. Right. Did that answer your question? All right. Ladies and gentlemen, I think it's cosmic question time. 8 minutes to the hour, and I think I should wrap up. If there's no other questions, was there one other? Yes, sir?
I just wondered if you were at all aware of Space War during that period.
Where was Space War?
Yeah, if you were aware of it while you were working.
Well, Space War was much older, on PDP-1s. It was developed, I think, at MIT and spread across the country. I was aware of it. At the Computer History Museum in Mountain View, California, they have a demonstration setting up live running Space War. And the people who designed asteroids were inspired by watching Space War. If you're aware of that arcade game. They were all aware of it. Does that answer your question?
Yeah, I just wondered if, like, Atari specifically were.
Well, we were aware of it. But the Space War was developed with a vector processor, and the arcade game was a raster processor, and the 2600 port of it is a raster process. The Atari 8-bit computer port is a raster process, not a vector process. Do you follow the distinction in how it's developed, how it's rendered? Okay. I think I need to allow all of you to go take breaks, have lunch, enjoy the rest of the show.
Thank you for watching. Please like and subscribe, and here are a few more videos for you to check out.